What I'm going to do in this video, I'm going to talk a little bit about constraint satisfaction and in particular Sudoku. So constraint satisfaction is maybe not the most glamorous topic we have in AI, but it's actually used quite a bit. And so it turns out that there are many problems that can be formalized as constraint satisfaction problem. So we will look at Sudoku. That's certainly one of them. Crossword puzzles is another game that can be formalized as a constraint satisfaction problem. Registering for classes. When you were sophomores, that was a bit of a challenging, wasn't it? Maximizing your GPA. I mean, there's only so much time you have in the day, and so determining where you're going to spend your efforts. Of course, chip design, where we're going to put things so they don't get too hot and they're fast and arrive in time. Any sort of optimization and satisfaction problem is a constraint satisfaction problem, such as planning. I mean, if you plan a trip somewhere, you have constraints such as financial resources, time, what you want to see, what you haven't seen, what you want to see again, building design, where we're going to put things, all the electricity, power, water, sewage, all those things. Any sort of scheduling problem can be formalized as a constraint satisfaction problem. All right, so what we will do is we'll try to explain this thing by having a look at Sudoku. I think most of you probably know Sudoku, but just very briefly, it's typically a 9x9 grid, but there are other problems. I mean, people have 16x16, 25x25, and I don't know if you don't have anything to do with your life. I mean, they're also 36x36. And there are different rules also, but the standards of vanilla Sudoku problem is 9x9. You have 9 columns, 9 rows, and then you have 9 subgrids, each consisting of 9 cells. And the objective is to fill all the empty spaces with numbers, in particular the digits 1 to 9. You can't have repetitions in the rows, columns, or in these boxes as they're called. So in other words, all the numbers 1 to 9 have to show up in this row, and in this row, and this row, and this column, and this box, this box, this box, and so on. So let's have a look at how we might want to solve this thing. So obviously there are many different solutions to this thing. We will have a look at a very, very basic way of solving this thing, and that's through backtracking search. It's not even close to what we would do as human beings. I'll talk a little bit about how humans might want to solve this thing typically in the next set of slides. So let's begin. Suppose we want to fill in this red cell over here. So as we know, we can't put the number 5, 3, or 7 in there because they already appear in this row. So those are out. Similarly, 8 already appears in the column, so we can't do that either. And then there's also 6 and 9 that appear in this box. So really the only values that we could consider for this one here are 1, 2, 4, and 7. Now, those are only choices at this point in time, and naturally they'll be reduced as we sort of like fill in these things. Again, I don't want to talk in this presentation about how we play this game. I just sort of like want to set you up to understand how a computer might play the game. So let's see. And the strategy that we are going to be using is called backtracking search. If you have seen searching algorithms, say in data structures or in some other courses, this is a variation of depth-first search. Again, a computer is fast and is super effective and efficient, and so we really don't have to think about this thing too much, or the computer doesn't have to reason or perform inference. It just sort of like has a fairly straightforward way of doing this thing. Let's so like briefly, before I talk too much about how we can solve this thing, let's talk a little bit about the formalization of a problem or constraint satisfaction problem, CSP. So what we have is we have a set of variables. In our case, it would be, each of these cells will be a variable. And then there are domains associated with each of the variables. Now in Sudoku, the domains are all the same. It's 1 to 9. Each of the variables has a domain of 1 to 9. And then there are constraints. And so the constraints are different ways of formalizing them. But the idea is, this one here can't be the same number as that one, or the same number as that one, or the same number, blah, blah, blah. And so we have like 8 constraints here. And then we have 8 constraints here and 8 constraints there. So not being equal would be one of them. So lots of constraints, but again, there are other ways of formalizing or representing this thing. Yeah, so we have done that. Involves the variables and defines relations among them. And in this particular example, I simply said this one cannot be the same as that one. But again, there are other ways of doing that. So the idea then is, in a constraint satisfaction problem, is we want to find an instantiation of a subset of variables so that they're all legal, they satisfy the constraints. Now we talked about some constraint satisfactions earlier today, that there's just no optimal solution. We just want to find a pretty good solution. So there'll be some sort of metric about when we're happy with a solution. But certainly for Sudoku, we don't have that. We want to find a valid solution, and we can do that there. So that's the objective. So a solution is an instantiation of all the variables in the problem, and it is legal if and only if it does not violate any constraints. So here's where it gets to be a search problem. So we start out with an empty assignment. Again, if we think about this problem over here, the given numbers we do not have to worry about. And so we don't have to, these would not be variables. Only the empty cells will be variables. So initially, we have no assignments to any of the empty spaces or any of the variables. So what we're going to do is we pick a variable and we make an assignment to it that doesn't conflict with any of the current assignments or any other constraints that are specified in the system. And then, we're done when the assignment is complete, when we assign something to all of them. So the interesting thing about search is that, or about CSP as a search problem, is that if we have n assignments or n variables, then we need to do n assignments. And it turns out it doesn't really matter which one we pick first. Now I should qualify that. If you want to write a very efficient constraint set or Sudoku solver, then yes, I mean, you want to probably pick some assignments over others. And again, we'll see that in the next slide presentation. But for the sort of plain vanilla backtracking problem solver that we're going to be writing here, it doesn't matter which one we pick first. So the path getting there is irrelevant. So in backtracking search, what we do is we look at the variables in some order. Again, for the problems, for the purpose of solving the 9x9 Sudoku, it doesn't matter. So we pick an unassigned variable and we give it a provisional value, but the value has to be consistent with all the constraints. The reason it's provisional is we'll see in a moment. If no assignment can be made, so we have a variable and then, no matter which value we pick, which digit we pick, we cannot satisfy any of the constraints, then we reach a dead end. And so what we need to do is we need to backtrack. And how we do that, we'll see in a moment. And so we continue this process until a solution is found, or we tried everything and we backtrack back to the initial variable, and we have exhausted all possibilities. So there's no solution then. So in the programming assignment, I actually have a problem that has no solution. And so I'll tell you more about that when I narrate that problem. So let's have a look at this, this problem over here. And what we do is we'll sort of like do this thing by rows. And we're going to look at the first row only. So 0 means nothing has been assigned yet. And so that's what we're going to do. We're going to go by row left to right. So what we're going to do is we're going to look at this one over here, 0, 2, 0th row, 0, 1, 2, this one over here. It had a value 0. So we're going to pick 1. So notice, let me go back to this one over here. There's no 1 in this row, there's no 1 in this column, and there's no 1 in this little box. So 1 is great. It doesn't violate any of those 3 categories of constraints. So great. Moving on then. So over here, again, we start with 1 as a value that we consider. And so, but 1 is already in this row, so we can't do that. So then we'll try 2. It's already in this row, so that's what we do over here. So I can't pick that one. I can't pick 3. Again, this one is still 0. So let's consider 4. 4 is still fine in terms of the row, but it's not good in terms of the column because we have 4 already over here. So let's have a look at 5. Again, doesn't violate the row, doesn't violate the column, and it doesn't violate the box. So we pick 5. So then we will move on. Let me move on to my slide presentation too. We look at this one over here. Again, we start at 1. 1 is already over here. We look at 2. That's already over here. We look at 3. It's already over here. Then we look at 4. Well, 4 is not in this row yet. It's not in this column. Notice it was in this column. And it's not in this square. So we pick 4. Great. We'll move on then. So then we'll look at this one over here. So we'll look at 0, 5, 0, 1, 2, 3, 4, 5. So we're done with this one. No, not yet. Let's see. This is where I wanted to be. I apologize. So we'll look at this one over here, and we'll try to put 1 in there, but we already have 1. 2, we already have that. 3, we already have that. 4, we have. 5, we have. Let's see. We have 6 in this box. Let's see. What else do we have? We have. Where's 7? Oh, wait a minute. I'm over here. We have 7. We have 8, and we have 9. So notice that at this point in time, we cannot assign a value to this cell over here. It violates all of the constraints. So what to do? What we're going to do is we're going to be backtracking. So we're going to go back to this assignment over here. Now look, and what we're going to do is we will have a memory of where we have been. So we won't start out with 1, 2, 3 again. We already know we did 4, so we're going to go up then. So we're going to say, okay, well, 4 didn't work because if I put a 4 in here, then none of these work. So we'll try 5. But 5 we already have. So we'll try 6. We already have 6, so we can't do that. So let's try 7. There's no 7 in here, no 7 in here, no 7 in here. So that's what we're going to do. We're going to put 7 in there. Okay, that's what we have over here. So then I will go forward again. And since we backtracked on this one over here, we will now start out on 0. So again, if we have to backtrack and we go back, we continue where we were. But if we then go forward again, we start out with 0. So we'll try 0. I'm sorry, with 1. So we already have 1. We have 2. We have 3. But we don't have 4. Okay, so again, this is the number that we're considering over here. And there's no 4 in this row, no 4 in this column, and no 4 in this box. So we put 4 in there. That's what we're going to do. So that's how backtracking works. Now, if for some reason or other we had run out of numbers over here, we would then backtrack to this one and try 6. All right, I'll see whether that works. Again, it doesn't. But that's kind of like the idea. And if we run out of numbers over there, we go back over here and we would try 2. All right, so hopefully that is that sort of like reminds you about how Sudoku works. So here's the backtracking search algorithm. It's from the Russell and Norvig AI A Modern Approach, the 2nd edition. So this is what you're going to be implementing. It's going to be a recursive procedure. And so you have a problem. How we're going to represent that, I'll say more in the other video about the programming assignment. But the idea is if we have made all assignments, then we will simply return the solution or the assignments. Otherwise, we select an unassigned variable, and then we try for each value, does it work? Okay, is the value consistent? And if so, we add it to the assignment. And then we call this thing recursively. All right. Now, the tricky thing about this problem is really what happens when we come back. And so that requires some thinking on your part and probably some fiddling. Because we return true or false. So if it's true, we're good to go. If it's not equal to failure, then we return the result all the way back, and eventually we get out of this recursion. However, if we were not able to find a consistent assignment, then what are we going to do? We got to remove this thing from the assignment. And the way we're going to do that is going to be slightly tricky. So that's what you have to worry about. And eventually, if we run out of values and we run out of assignments, we return failure. All right, so that's a little bit about the conceptual aspect of backtracking and Sudoku. And so in the next video, or in the video about the Sudoku assignment, I will say a few things about how you might want to implement this thing. All right, I'll see you then. Bye.